Hi, I'm Hannah, and today I'll present our schema inference method for property graphs. This is joint work with Angela Bonifati and Russ Harmer. So property graphs, or PG for short, are used to store information as a graph, such as in graph-based database systems or to model complex systems like the brain or social networks. However, most of the time, PDs are built without first predefining a schema, even though schemas provide crucial information, such as the structure of the graph or different kinds of constraints. So this is where schema inference becomes an important tool. As it happens, PGs and PG schemas are currently in the process of being standardized, and as far as we know, there are very few PG schema inference methods available, and the few that do exist come with very basic features. So we propose here a new PG schema inference method that actually handle multiple labels and complex data types. We also infer non-hierarchies, edge cardinality constraints, and the optionality of properties. Moreover, we developed the corresponding Python pipeline, which is available on GitLab, and we also empirically evaluated the scalability and quality of our method on real-world datasets. So let's go on and define property graphs. So you can see here a formal definition that can be found in the literature, but basically, a PG is a directed graph where nodes and edges can be labeled, and they also can hold properties, which are key value pairs. So for instance, here we have a node labeled person and patient, and it has a property with a key name and the value Alice. So now let's define PG schemas. So today I will only introduce the key concepts needed to understand the rest of my presentation, but you can find the full definition in our paper. So a PG schema is a triple that's essentially a PG that defines which node type and edge types are allowed. And unlike in a regular PG, the property values in the schema are data types like string or number. And in this schema, edge types are defined by their source node type, target node type, and the arc linking the source and target nodes. Edge cardinality constraints are also defined. So for example, here, this edge has a many-to-many relationship, meaning that the patient can know many doctors and a doctor can be known by many patients. And in order to tackle node hierarchies, we also need to introduce a few additional concepts like subtypes, which can be defined as types that inherit from a supertype. So for example, here, a doctor is a subtype of person. In order to embody the relationship between a subtype and its supertype, like you can see here in this example, we also need to introduce a special edge type that we call the inheritance edge type. So now I'll present an overview of our PG schema inference method. So as an input, we have a PG, and we want to infer its schema. So to do so, we have to infer the types and data types, the edge cardinality constraints, and the node type hierarchies. To identify the types and data types, we leverage a MapReduce-based method that was developed a few years ago for JSON datasets. One of the main challenges here is to convert the input PG into a JSON format that guarantees proper type inference. Moreover, this MapReduce method does not tackle hierarchies, so this had to be dealt with separately. So to sum up, we have a first step where we query the graph to match all the nodes and edges, and we convert them into an appropriate JSON format. And since we're already going through the entire graph, we also infer the edge cardinalities at the same time. Today, I'm not going to detail how we do that, but this is explained in our paper. As a second step, we infer the types and data types, and from there, we convert the output of the MapReduce algorithm into the format needed for the node hierarchy inference, which corresponds to our last step. Once we've got the node hierarchies, we actually have our output PG schema. We have developed two variants of this schema inference method. The first one is based on the assumption that labels characterize types. However, when we only consider labels, we're actually missing out the information provided by the properties. So this is why we introduced a second variant where the property keys are the one to characterize the types. In this presentation, I'm going to focus more on the label-oriented variant. So now let's detail the first two steps through this example where we have two nodes that are both labeled person and patient. In the first step, we extract the labels and properties of each node and store them into dictionaries where the key consists of the labels, and the value is itself a dictionary corresponding to its properties. We repeat the same process for edges, and then we go on to the second step, that is actually divided into two phases. First, we have a map phase where from the dictionaries we just obtained, we infer all of the property value data types. So for instance, the value of the property address is an array of strings. Then once we have all of the property value data types, we have a radius phase where we aggregate all nodes and edges by type. And to do so, we recursively fuse dictionaries with dictionaries, arrays with arrays, and so on and so forth. The value of two dictionaries are fused together if and only if they have the same key. So that means that two nodes will be fused if and only if they have the same labels. Like in our example here, both nodes are labeled patient and person, so they're fused together into a single patient-person node type. Their properties, which are stored in dictionaries, are hence fused together. If one of the dictionary contains keys that are not present in the other, then this particular key value pair is considered optional, like here with the student number property. So to recap, after the first two steps, we have inferred from the input PG an intermediate schema where the nodes and edges have been aggregated by types via their label sets, and the data types and edge cardinality consents have been inferred. We're currently only missing the node hierarchies, which corresponds to our last step, which can actually be divided into two phases. First, we infer the supertypes by a pairwise intersection of the label sets. In the example here, the labeled person is included into the label sets of three different node types. So we identify a node type labeled person as a supertype. Then we identify subtypes and the corresponding inheritance edges. And to do so, we consider that a node type is a subtype of another node type if their label sets are included into one another. So for example, here, person, doctor, patient is considered to be a subtype of person, doctor. So I mentioned earlier that we had considered a second approach to the schema inference, where we consider property key sets instead of label sets to infer node types as well as subtypes and supertypes. In this variant, labels are actually considered to be special properties, so unlabeled nodes can be taken into account. In addition, during this type inference step, property co-occurrence information is identified, but this is done at the expense of the inference of the optionality of properties. So now let's compare the schemas obtained from the same input PG via these two variants. So we can notice in the schema obtained by the property-oriented variant that two node types with the label person and patient have been inferred, while only one such type was inferred with the label-oriented variant. This is because some of its properties, like student number, are only present in some of the nodes of the input PG. So this additional node type hence tells us that there are two types of patients, students and non-students. But in the process, a spurious post type was inferred. So we need a trade-off between these two approaches. To validate our method, we experimentally evaluated our schema inference method on two flight brain networks, a COVID-19 graph, and a social network. Some of them had ground truth schemas, so in these cases, we were able to calculate some metrics like the precision and recall. And the main insights we got here were that the label-oriented variant has a very good precision, but it is missing the node types that can only be inferred through the property-related information. So this is actually partially overcome by our property-oriented variant, but this is done at the expense of the precision. Indeed, we're now inferring spurious types. We also conducted a scalability analysis by obtaining the average running times for different sizes of the datasets, and the total running time is dominated by the first step. And this is because the queries to match the nodes and edges cause an overhead that increases with the input size. On the bright side, the running times of this step seem to be at worst linear with the input size. For the second step, the running size is sublinear with the input size. And finally, for the third step, the running time is actually constant with the input size. So to conclude, we have proposed here a new end-to-end PG schema inference method that tackles, amongst other things, node hierarchies. We have also developed the corresponding Python pipeline and evaluated it on real-world datasets. We have introduced as well two scalable variants that both output schemas of overall good quality, but they both come with their advantages and drawbacks. So as future work, it will be interesting to combine the outputs of the label and property-oriented variants. And Our method is also sensitive to variation in the label and property key names. So as future work, it would be worth exploring machine learning solutions or statistical approaches like clustering, maybe combined with graph embedding for the type inference step in order to try and overcome this sensitivity. So thank you